All right. If you have a base a and it's being raised to an exponent that is a log with the same base a as the base of the exponent, does that make sense? The base a and the logarithm base a undo each other. You have that same m left. Okay. And then same goes for if the log is down here and the base is here. Good. Log base a of the base a raised to a power leaves you with that very same power. If these were examples with numbers, you would be able to put them into your calculator and see that it is true, right? So if I said 9 to the power of log base 9 of 8, and I put that into my calculator, nine to the power of oh no. Log base 9, so that number and that number are the same, of anything, right? Of 8 is going to give me the number 8. So when that base and that base are the same, your answer is whatever you were taking the log of. Let's do the other one. The other one would be something more like log base 6 of 6 to the power of 7 should give me log base, what did I write? 6 of 6 raised to any power is just going to give us that number back. Good. All right, so those are the first two rules. Here, these last three, this is where we're going to learn how to, again, I already said it, expand and condense. Why? On the left, these are condensed, right? These are the expanded form, but they equal each other. We will be able to go between condensed form and expanded form. This leads to the ability to solve more complicated logarithmic functions. And then because we know how to convert between exponential functions and logarithmic functions, we can solve more complicated exponential functions as well. So the first one of that set is when you have a log of things being multiplied, m and n, the product of m and n, you can expand it by taking the log of each individual part and adding those logs together. So we're taking the log base a of m times n. You can also say that that is equal to log base a of m plus log base a of n. Good. Next one, the log base a of m over n can become the log base a of m minus the log base a of n, right? You can take the log of a fraction and expand it by taking the log of the numerator and subtracting the log of the denominator from that. And finally, the last one is if you have the log of something being raised to a power, that little r right there, you can bring the exponent down in front of the log and multiply it. So right now it's just m is being raised to r. We can put the r in front of the whole situation and multiply it as a constant with the entire log. Okay. The last, so 6.6 is just simplifying or solving complex exponential and logarithmic functions or expression. All right. First example here, we have 3. raised to log base 3 of pi, right? Our rules say that a base being raised to an exponent that happens to have the log of the same base will cancel itself out, right? So this is the rule: a to the power of log base a of m equals m. That's the rule we're using. And what we have is 3 log base 3 of pi equals, so here a was 3 and m was pi. So we have 3 log base 3 of pi is pi, right? Okay. You can even check your answer. 3 raised to the power of log base 3 of pi is pi. Good. All right. Second one, same exact scenario. A to the power of log base a of m is equal to m, right? 7 raised to log base 7 of 3. The 7s cancel, and we are left with what we were taking the log of, which was radical 3. If you put it into your calculator, you will find that 7 to the power of log base 7 of anything, but in this case, square root of 3, will give you that same square root of 3 as your answer. All right, what about this one? The natural log of e to the power of negative 13. Remember that the natural log can also be written as log base e. So the natural log of e is the same as log base e of e to the negative 13. So what rule are we using now? Now we're using that second rule. Second rule says that log base a of a to the power of r is going to leave us with the r. So natural log of e to the power, or sorry, raised to negative 13 is just going to leave us with negative 13. Example 2 is a little bit more complex, right? We are going to now expand. Remember, we are using these rules to expand. This is the condensed version. We're going to expand it. We have log base a of x squared times, right, the square root of x plus 1. I'm going to rewrite this as log base a of x squared times x plus 1. Oops, way too many parentheses now, right? So we have 2 separate terms that are being multiplied, right? We also have some powers that if we're taking m to the power of r, we can bring r out in front, right? Okay, so we have x squared times the square root of x plus 1. I'm looking at a single log, the log base a, of 2 terms being multiplied together. A log of 2 terms being multiplied, you can separate them by taking the log of each and writing it as a sum, right? That rule is, I'll write it down. The rule we're using here is log base a of m times n can be expanded to log base a of m plus log base a of n. So this can become log base a of x squared plus log base a of the square root of x plus 1. What other rule might apply? So we applied this rule to expanding it. What second rule could we use? We can use that third one, right? Log base a of m to the power of r becomes r times log base a of m. All right, so before we do that, I want you to think about what the square root symbol means. Good. The square root of x is the same as x to the power of 1/2, right? The third root of x is x to the 1/3. The fifth root of x squared is x to the 2/5, right? So if we wanted to use the rule for expanding when there is an exponent, we can call the square root of x plus 1 x plus 1 raised to the 1/2 power. Okay. So I'm going to write it again. And instead of a radical, I'm going to call it an exponent. It's not the square root of x plus 1. It's x plus 1 raised to the power of 1/2. Now I'm going to use the rule. Where should I start? Log base a of m to the power of r is the same as r times log base a of m. I'm going to apply it to this one and to this one. So this one, my r is 2. This one, my r is 1/2. They each go in front of the log. So we have 2 log base a of x plus 1/2 times log base a of x plus 1. So that would be how you would expand an logarithmic expression. Example 3, we have the natural log of a fraction, right? Log base e of x squared over the quantity x minus 2 to the 4th, right? We have the rule that a log-based fraction can be written as, so we know that log base a of m over n is log base a of m minus log base a of n, right? Log base a is just natural log, because natural log, as we know, is log base e. So the natural log of x squared divided by the quantity x minus 2 to the 4th is going to be, I guess I'll write it. So the natural log of all of this becomes the natural log of x squared minus the natural log of x minus 2 to the 4th. Good. Last thing we're going to do, move that 2 and that 4 out in front based on that rule. So the natural log of x squared minus the natural log of x minus 2 to the 4th becomes 2 natural log x minus 4 natural log x minus 2. Very crooked. But there is the expanded form. Okay, here we have log base b of a fraction, the cubed root of x squared plus 2 over x squared times x plus 2 squared, right? So just like we said that this can be written like this, we also know that the cubed root of this can be written as x of 1/3, right? Okay, so I'm probably going to change the cubed root to an exponent. So I'm going to rewrite this as log base b of x squared plus 2 to the power of 1/3 over x squared times x plus 2 squared. I'm going to use this rule before I use this rule to expand. So that rule says I can subtract, right? So now I have log base b of x squared plus 2 to the power of 1/3 minus log base b of x squared times x plus 2 squared. Now, wow, I really can't draw in a straight line today. Right in a straight line. So now, if you'll notice, we've used this one, right? There's no more fraction. We can use this one, right? But there's something we can use before that. I see that these two are being added, but these two terms are being multiplied. So we can expand this even further because our goal with this one is, right, as a sum and difference. So all we're doing is expanding. So I see x squared being multiplied by x plus 2 squared. So that's the same as m times n, right? So I can write all of this as another addition problem. So we'll keep the top of the fraction as log base b of x squared plus 2 to the 1/3. But then I'm going to subtract all of the following. I'm going to subtract log base b of x squared times x plus 2 squared is going to become log base b of x squared plus log base b of x plus 2 squared. Right? Let's go ahead and distribute that negative before I forget to distribute the negative. So all of that will become log base b of x squared plus 2 power of 1/3 minus log base b of x squared minus log base b of x plus 2 squared. Distributed the negative. Now, finally, I move the exponents down in front. So I have a 1/3 here. The last thing I can do is move the exponents. I have a 2 here, and I have a 2 here. So final answer is I'll do it down here. 1/3 log base b of x squared plus 2 minus 2 log base b of x minus 3 log base b of x plus 2. 1/3 log base b of x. Nope. I don't know why I called that a 3. That's a 2. It's that 2 right there. All right. So you started with a log of a polynomial, right? There's a lot going on here. A polynomial fraction, and we expanded it. So now it is the difference between 3 unique logs, and all of them are in, right? There's nothing being multiplied or divided. So that's the goal as you expand. The last example 5, we're just going to go from condensed. Sorry, we've been going from condensed to expanded. Now we're going to look at the expanded and see if we can condense it into a single logarithm. So we're going to use these 3 properties as we have been using them to write each of these as a single logarithm. A is log base b of 5 plus 3 log base b of 2. Think about the order we do it in, right? We always use this step last. So, hold on, getting ahead of myself. Let's just write it down. Log base b of 5 plus 3 log base b of 2, right? Okay, we've got our properties. We're going from this side to that side now, from right to left. So our final step was always, when we were going the other direction, was to bring the exponent down in front. So when going the opposite direction, it's going to be the first thing we do. So these are both log base b, so we can combine them. The first thing we're going to do is find anything that's out in front of the log and put it back as an exponent. We're condensing, right? So this doesn't change. This remains log base b of 5 plus, instead of that 3, log base b of 2, we're going to call it log base b of 2 to the power of 3. Good? All right. They're both base b and they're being added. That means they're being added. So now we can combine them via multiplication. Log base b of 5 times 2 to the power of 3. You're also welcome to have worked that out to 8 beforehand if you want. So basically the simplest form, the single logarithm, is going to be log base b of the number 5 times 2 to the third. 2 to the third is 8. 8 times 5 is 40. So log base b of 5 plus 3 times log base b of 2 becomes log base b of 40. The next one is 2/3 of the natural log of 27 minus the natural log of 6 squared minus 9. Good. Let's move the 2/3 back to exponent position. So it will become the natural log of 27 to the power of 2 over 3, right? Now we have 2 natural logs being subtracted, right? They have the same base, natural log or log base e, and we can condense subtraction into division. So that's going to be 27 to the power of 2 over 3 divided by 6 squared minus 9. (27 to the power of 2/3) is 9. Six squared minus 9 is 27. So we're taking the natural log of, sorry, red room. The natural log of 9 divided by 27 is the same as 1/3. And you don't have to do it in the order I did it, but in terms of like simplifying this. You could simplify all that and then put it into a fraction form. Last one. We have, oh, they were letters and I was putting them as numbers. I have log base b of x squared plus 4 plus log base b of 4 plus log base b of x minus log base b of 7. The first three are being added. So I'm just going to multiply those all together. And then this one's being subtracted. So I'll put them all on top and I'll put the 7 on the bottom of a fraction, right? So I'm going to use this rule first. When I'm combining them and they have the same base, log base b, I can put them all in one log and multiply them. So that is now log base b of x squared plus 4 times 4 times x minus log base b of 7. So just like I said, you don't need to do my order like this. I'm going to multiply this now to get it into its simplest form, not factored form. So x squared plus 4 times 4 is just going to be 4x squared plus 4 times x. I'm doing these one at a time. You can do them all together if you want. Log base b of 4x to the third. Oh, sorry. 4 times 4 is not 4. It's 16. 4x to the third plus 16x, right? Minus log base b of 7. So final step is to go from subtraction to division. They have the same base b, so we're just going to call it log base b of 4x to the third plus 16x over number 7. Good. All right, we're going to, in our last class, solve complex logarithmic and exponential functions, and that is why we practice all of this today.